Our next unit of study will cover the topic of momentum, which along with energy forms some of the most fundamental laws in all of physics. So, what is momentum? Often it's defined as a quantity of motion. What exactly that means, well, who knows. But mathematically, we define momentum as the mass times the velocity of an object. We use the letter P for momentum because m is already used for mass and a variety of other things. So it's also lowercase p as opposed to a capital P like you use for power. The direction of the momentum vector is in the same direction as the velocity. So you can have positive and negative momentum just like you can have positive and negative velocity. Let's compare this to the other quantity of motion that we are already familiar with, and that is kinetic energy, 1/2 mv squared. And you might ask, why do we need another quantity of motion when we already had one? And that's because the two have different properties that allow you to solve different types of problems. If you're a scientist, sometimes you can only measure certain things, and if you have these two quantities working together, you can solve for more things that you didn't know than just with kinetic energy. Another thing to point out, the difference between the two, we just mentioned momentum is a vector quantity. Kinetic energy is a scalar quantity. So that means that with momentum, you can start out with zero momentum as long as you create an equal amount of momentum in one direction as in the other direction. So we could call this the negative momentum this way. As long as you create equal amounts, you can get as much momentum as you want starting with no momentum. You can't do that with kinetic energy because kinetic energy in one direction is positive and in the other direction it would also be positive. So it's not canceling out. You can't start with zero kinetic energy and just create positive and negative kinetic energy. It doesn't work that way. Now you could think of some other quantity. You could call it, I don't know, quantity z, that is some strange number, 4/7 m cubed v, and say, oh, I'm going to make a third quantity of motion and try to get everybody to use it. The problem is this guy is not going to have any useful properties, not likely anyway, whereas these guys do. For kinetic energy, we already know that it can be transformed into other types of energy, and it's part of the greater conservation of energy law. With momentum, we have a conservation of momentum law. Conservation. And this is in a way more powerful than kinetic energy because we don't have a conservation of kinetic energy all by itself law. There's no law of conservation of kinetic energy. It's just law of conservation of energy. So that's another thing that makes momentum useful in certain situations where kinetic energy alone is not. So just like with conservation of energy, we can say that the initial momentum of a system equals the final momentum of a system, and as long as your system includes everything that's interacting, your initial momentum will always be constant, or your total momentum will always be constant. Now you can create positive and negative momenta where there was no momentum before, but the sum has to remain constant. And often we write this as an interaction between two objects, though it could be an interaction with a large number of objects as well. But if we have two objects interacting, we would say that the initial momentum of object 1 plus the final initial momentum of object 2 equals the final momentum of object 1. And a lot of times, well, your text anyway uses this prime notation for the final, just so we don't end up with a million subscripts. So that's the final momentum of object 1 plus the final momentum of object 2. And as I mentioned, some of these could start out 0. This entire side could start out 0, in which case their final momenta would be equal but opposite in direction when you subtract one to the other side. And if we go ahead and plug in masses, this is going to be m1v1 plus m2v2 equals m1v1 prime plus m2, that's a big 2, but you get the idea, v2 prime, where we're taking the masses to be constant, which is usually the situation. And then these primes again indicate final velocities and initial velocities. Alright. Something else we can look at related to momentum, if we start with the Newton's second law of motion, F equals ma, and we rewrite that acceleration as the derivative of velocity, then we pull the m into that derivative because, as I mentioned earlier, it's typically constant, so you can pull any constant in or out of a derivative, dv dt, and this d of mv is just change in momentum over time. We can go ahead and make these vector quantities here. So this is another definition for force, change in momentum over time, or the rate of change of momentum. And this is actually how Newton originally defined his second law, not in terms of mass and acceleration, but in terms of the rate of change of momentum. He also considered momentum similar to kinetic energy, and it took him a while to figure out that those were separate things. But anyway, if we are not interested in the instantaneous change, we can find the average force by doing the change in momentum, delta p instead of dp, over delta t, which we usually leave off the delta since the initial time is 0, and this is often rewritten as force times time equals change in momentum, which can also be written as m delta v, again assuming that the mass is most likely going to be constant. So this makes up one of the two main approaches, or most common approaches, and this is the other to the types of problems that we will solve. A lot of problems will be conservation of momentum problems, where we're applying an idea like this, and then a lot of problems will be force change in momentum problems. So depending on what information you have, if all you have is mass and velocity information, you're going to be using something like this. If it tells you something about forces or time, you're going to be using something like this. Alright, let's get to a few examples here. Here we've got a rocket that has initial velocity of 0, initial mass of that, shoots out that much in exhaust gases at 700 meters per second, and we want to know the final velocity of the rocket. So as I just mentioned, we've got two main approaches that we're going to choose from depending on the information we have. In this case we have mass information and we're interested in velocity information, no forces or time, so we're going to use conservation of momentum. Initial momentum equals final momentum. The initial momentum is 0 because nothing is moving. The final momentum is the momentum of the rocket plus the momentum of the gases. So you can subtract one to the other side and they will be equal in magnitude but opposite in direction. So then we can plug in the mass of the rocket times the velocity of the rocket. It's an ugly R there. Equals negative mass of gases times velocity of gases. If you want to put these as primes, I guess you could do that. It doesn't matter too much when there's not other v's to distinguish them from. The mass of the rocket, now since this is the final state here we're looking at, we can't take the entire 4,200 initial mass of the rocket. We have to consider the mass of the gas that was ejected. So this will be 42,000, I think I said 100. Anyway, 42,000, we have to subtract off the mass of the gas because that is no longer part of the rocket times the final velocity of the rocket. Then here we've got the mass of the gas that went flying out, so 5,800. We can have a negative sign there. The velocity is 700 meters per second. If we take this direction to be the negative direction and that to be the positive direction, then we need to make this negative 700. And then we do a bit of algebra and we can solve for the final velocity of the rocket. It comes out to be 106.3 meters per second in order to conserve momentum. If all we had were kinetic energy to consider, if we didn't know about momentum, this problem would not be possible. We would need other information as far as the energy released and whatnot. Okay, another example. Here we have one of the last decent American tennis players, at least on the men's side, Andy Roddick here serving a ball, and if we assume he serves it at 55 meters per second, he could actually serve it at close to 150 miles per hour, I believe. Anyway, the ball is 60 grams and the racket is in contact for 4 milliseconds. What is the force on the ball? So obviously we have forces and times involved here, so we'll use the equation Ft equals m delta v. And if we solve this symbolically first, we're interested in the force, so m delta v over t, and then just plug in our numbers, 0.06 delta v. It went from 0 to 55, so that's a change of 55, and the time is 4 milliseconds, 4 times 10 to the negative third. Throw that guy in your calculator and you get 825 newtons of force. And then it asks, would this be large enough to lift a 60 kilogram person? Well, just doing a rough estimate, 60 kilograms is going to take a little bit less than 600 newtons to lift, and this is well over 600 newtons. So yes, it could lift a 60 kilogram person for an entire 4 milliseconds, so not going to lift them very far, but it would certainly make them move. Alright, a couple other examples. If we have the momentum of a particle given by this equation here, where I, j, and k are just the x, y, and z directions, these are what we call unit vectors, and we want to know the force acting on the particle, well, we have the relation that the force is dp dt, and so we just got to take the derivative of this guy with respect to time. And since we're not taking the derivative with respect to, there's no x, y, or z components. Well, they're components. There's no x, y, or z variables in here, so we don't call this a partial derivative. We're just taking the derivative of this whole thing with respect to time, and these are the directions of each of these components. All right. So the derivative of this guy just leaves us with a 5.2 in the I hat direction. Derivative of this guy goes to 0, and the derivative of that guy is going to give us a negative 6.9 t squared in the k hat direction. So that's all there is to it. You just have to take the derivative with respect to time. Piece of cake. One more question here, a conceptual question. So you've got a sled sliding along, an unmanned sled apparently. Susan drops vertically from a tree onto the sled. When she lands, does it speed up, slow down, or keep the same speed? Take a second to think about it. And the answer is it will slow down because you have added mass without adding momentum. So if you were going to calculate it, you would have the mass of the sled times its velocity equals, so this is our initial momentum. You would set that equal to the final momentum, which is the mass of the sled plus the mass of Susan. All of that combined to a new velocity. This is going to be, I guess we'll call it v prime. This is going to be a bigger mass. You can divide that and this will come out smaller. Another way to think about it is as Susan falls straight down, here's your sled with some nice runners on it, and Susan is now a box. As she falls straight down, she doesn't have any horizontal motion, whereas the sled does. So in order to make the box move with the sled, hopefully there's friction, right, or she grabs onto the sides or whatever, the sled is going to need to exert a force forward on Susan, which means Susan needs to exert a backwards force on the sled, and so that will slow down the whole system in order to get her up to speed. Now, a little bit later, she falls off the sled sideways, so just kind of rolls off or tips off the sled. Does that make it speed up? You've probably got enough experience in the world to know that rolling off something doesn't make it automatically go speeding off. So it will have the same speed. In this case, when Susan jumps off the sled, so here's our box rolling off the sled this way, it exerted a horizontal force on the sled, so maybe there was a frictional force on the snow pushing the sled that way. Well, no, she pushed the sled that way, and the friction would like oppose that so that it didn't move too much laterally. But there was no force forward or back, so that's not going to change the speed of the sled. And in fact, when she first rolls off, she's going to keep moving in the same direction that the sled was moving. So velocity, these were forces we were talking about. Until she hits the snow, then she's going to transfer some of her momentum to the snow and slow down and stop. But the sled will just keep going in the absence of any friction. All right, there is